Okay, good evening, everyone. Welcome to week 7 problem solving session for selected topics on algorithms course. And my name is Bhavya. Okay. I'm a PhD from IIT Madras. Okay. And as always, we'll have these sessions Tuesdays 6 p.m. to 8 p.m. Okay. Okay. So I will begin by discussing the previous assignment questions as always. Okay. But uh, the previous assignment questions, there was a slightly overlap between this week's content. And what is this week's content? Uh, this week's content was uh, what is called complexity, okay, or computational complexity, and some complexity classes, which we only dealt with P, NP, and coNP, and hardness and completeness. Okay, that is, we learned what is NP hard and NP complete. And finally, some and reductions and examples of NP complete. Okay, so this is this week's content. So a lot of terms floating around, but don't be afraid of it. So it's actually a very nice way to categorize problems. So we'll come to it. Okay, so let me just yeah, I think it is better that I first explain these and then move on to the problem set questions. Okay, now um, I'll the first two questions. Okay, I will not solve for now because it depends on these completeness hardness concepts. This the last two questions 8 and 9 in the previous assignment. Assignment 6, I will do. I'll tell you the solution. So question 8 says, what is the number of independent sets of an undirected graph with 10 vertices and 1 edge? Okay. So mm, so what is an independent set? So independent set is a set of vertices, okay, of graph G is a set of vertices which is let me call it I. It is a subset of um, vertices of G such that for all pairs between U and V there does not exist an edge. Okay, what does it mean? For example, um, here is a graph, okay, and I'll call it 1 2 3 4 5, okay, and something like 1 3 okay, 1 3, and that's it. 1 3 is an independent set because there is no edge between 1 and 3. Okay, similarly 1 and 5 is an independent set. Okay, and can I make a bigger independent set? Is also an independent set. Can I make a bigger independent set? Well, I can. Looks like I cannot, right? Because if I choose, let's say, 2 along with 1, then 1 and 2 has an edge between them. If I choose 3, I cannot add any more. If I add 2, 4, or 5, it will always be adjacent to 3. Okay, so but something that's why something like 1 3 5 is not an independent set. Okay, so that is an example. Because why? Because 3 5 is an edge. Okay, now, so I hope this is clear. And this also asks, so just a small digression here. This also asks, what is the maximum size of independent set I can get? Okay. I can construct in a graph. Okay, now this is the first question, and this is another question. Okay, what is the minimum size independent set? So which do you think is an easier problem?
So the maximum one is the difficult one, and the minimum one is the easier one, because in an independent set there could be an empty set also, wherein there is no vertex and no connectivity.
Okay, that's good. Yeah, it could be. So for example, empty set is also an independent set, and something, if you say, like, if you give me an empty set, then it is cheating. Then I can also say, just a single vertex is also an independent set. Okay, and so minimum size independent set is easy. Okay, so what about maximum size independent set? That may not be very simple. Okay, and we'll talk about that later. I just wanted to add this question here, but we'll come back to it. We'll come back to the question: what is the number of independent sets of an undirected graphs with 10 vertices and 1 edge? Okay, so let's look at the question. Okay. Solution. Okay, G, that is a graph. Okay, VE, and this number of vertices is 10, number of edges is 1. Okay, and so assume, so let's say this is your graph, v1, v2, v3, and so on till v10. Okay, so let's say v is v1, v2, and so on till v10. Okay, good. Now what do you want to do? You want to count the number of independent sets, remember, and you are saying that the graph size is 10 and there is one edge exactly, okay, sitting inside the graph. Okay, good. Now it could be between any vi and vj, but for the sake of simplicity, let's assume that the edge is between v1 and v2. Okay, without loss of generality, assume that v1, v2, okay, that there is only one edge, that is the edge set is an edge between v1 v2. Okay, so rest all are isolated vertices. Great. Okay, so now what do you need to do? You want to count the number of vertices, the number of sets, such that there are no two vertices that have an edge between them. That is the definition of independent set, right? This is the definition of independent set. All the subsets of vertices, take any subset of vertex, it should not be that there are two vertices such that there is an edge between them. But what do you realize? Okay, let me take an example. Let's say I take v1, v3, v10. This is an independent set. If I take v9, v10, this is an independent set. Even if I take something like v2, v3, v4, this is still an independent set. None of them have an edge between them. But notice that the moment I take v1, v2, v3, this does not become an independent set, because there is an edge between which is the only edge in the graph according to the question. Okay, because there is an edge between there is edge between v1 v2. Okay, good. So now all I want to do is, okay, so now what does this mean? Okay, need to count a number of subsets of v that do not contain both both v1 and v2. Okay, need to count the number of subsets of v that do not contain both v1 and v2. Now there are quite a few ways to do it, but let's do a simple counting argument. Okay, so this count the number of subsets that do not contain. Okay, so number of subsets, okay, that do not contain both v1 v2, okay, is equal to, okay, go ahead, listen to the rate. Okay, let's okay, I'll explain that. Yeah, thank you. Okay, so number of subsets that do not contain both v1 v2 is equal to, okay, 1 minus number of subsets, not 1 minus, sorry, total number of subsets minus number of subsets that contain v1, okay, not v2, and this is, let's say, a whole minus, okay, plus number of subsets that contain v2 not v1, okay, or number of subsets that does not contain v1 as well as v2. Okay, so this is one way to count it. Maybe you can do it directly also, which is not a problem. Okay, but I want to clarify the intuition between about it. So what is the total number of subsets? Okay, what is the total number of subsets? What is the total number of subsets of v? This is simply the what is called the power set, right? Of, yeah, which is 2 to the 10. The size of the power set is 2 to the 10, right? What is the logic behind it? There are 10 elements. Okay, there are 10 elements. I have 2 choices for each element. Either I put it or I do not put it. So that contributes 2. And I keep doing a product. Okay, I have 2 choices for the first element, 2 choices for the second element, and so on. Okay, so which is 2 to the 10. Okay, that is total number of subsets of v, which is 2 to the size of v, which is 2 to the 10. Okay, so that is the total number of subsets. Now minus the number of subsets that contain v1 not v2. Okay, so let's see, that contain v1 but not v2. Number of subsets that contain v1 but not v2. So let me call this sum as s1. Okay, let me call this as s1, let me call this as s2, and let me call this as s3. Okay, so what is s1? Number of subsets that contain v1 but not v2. S1 equals to total. Okay, it should contain V1 but not V2. So what is that equivalent to? That is equivalent to total number of. Okay, there is an overlap, right? Okay, no, that's fine. Total number of subsets of this that it should definitely contain V1. Okay, so we fix V1, and the remaining places should be fixed by uh, V3, V4, and so on till V10. Right? I can V1. I should definitely choose, and these I can either choose or not choose. Okay, and S2 is again total number of subsets of fix V2, but I'm not allowed to choose V1. It should contain V2 but not contain V1. So V2 I fix it, and I choose whether to include V3, V4, and so on till V10, but I do not allow V1. Okay, and finally, what is S3? S3 do not contain V1 as well as V2. So that is total number. So this is a classic, permutation, counting combinatorics question. Subsets of do not contain V1 as well as V2. V3, V4, and so V10. Okay. Okay. So what is the answer? So, and how many elements are here? 3 to 10. Okay. There are 8 elements. So 2 power 8. Number of subsets. Okay. 2 power 8. There are 8 elements, right? 3 from V3 to V10. And yeah, that's correct. No? 2 you are removing. So yeah. So here also 2 power 8, because again the size of this is 8, and here you have total number of subsets of V3, V4. You're not fixing. Okay, so this contain, that does not contain as V1 as well as does not contain V2. So this is also 2 power 8. There is some problem here. Yeah, Kishore.
Probably, I think for S2 or S1, right? It should be, see, number of vertices are 10, and then as per the S1, V1 should not be available. Then it should be 1 minus 10, or 10 minus 1 is 9. It should come, right?
Which one? Which part?
The S1 and S2, both. Yeah, both.
S1 and S2, total number of subsets. See, V1 should definitely be, we should definitely choose V1, but we should definitely not choose V2. So V1 we are
Right.
keeping separately and saying that V1 will definitely be there.
Okay.
Okay, and V1 should definitely be there. And what we are doing is we are choosing all possible subsets from this set, which does not contain V2. So the resulting all the subsets that I get on doing V1 union all the subsets of this will characterize exactly this sum. It will contain V1. Okay, it will contain V1, but does not contain V2.
Yeah, but that, see, the number of vertices will come as 9, right? The resultant.
Why? Because we have V3, V4, and so on till V10. This I'm counting, and I'm only to each of them I'm just attaching V1. So number of sets will remain the same. Number of subsets. See, there are 2 to the 8 subsets of this. To each of them, I'm adding V1 there.
Okay.
So number of subsets will remain the same.
Okay.
Okay, Goel says I changed my answer as 8C2 times 2 power 8. Okay, let's see. Okay. Okay, let's see. Now 2 power 8. Okay, and okay, so that's what I'm saying. I'm sorry if it was not clarified well. What I mean to say is, here I'll choose all possible subsets of this set. Okay, and there, to each of those set I'll put a v1. To each of them I'll include v1. So this will, what will it result in? It will be the set of all subsets. Okay, it'll have all subsets that will definitely contain v1 but will never contain v2, because I never considered v2 at all. Okay, so but see, the count will remain the same because I'm not adding any more sets to it. Okay, so it was 2 to the power 8. There are 8 elements here, and to each of them I include v1. So what do I get? To each of the sets I include v1, so we are not increasing the number of sets. Okay, and this is what we have. We get 2 to the power 8. Okay, and here too we have 2 power 8. Same logic. v2 we fix. The remaining places, okay, the remaining places I put subsets of this, which will never contain a v1, and which is again 2 power 8, and total number of subs. Okay, now what? So you could have v1 there, or you could have you could have v1 there but not v2, which is shown by this. You could have v2 but not v1, which is shown by this. Now the final case is, you could have chosen neither v1 and v2, in which case the number of subsets is still same, 2 power 8, because you're not including anything here, anything into the subsets, but still the count is the total number of subsets of v3, v4, and so on till v10. Well, this set will never contain any subset of this will never contain both v1 and v2. Either v1 or v2 or both v1 v2. All three cases are not possible, right? Which is again 2 power 8. So therefore, what do you get? We get the answer is 2 power 10 minus 3 times 2 power 8, right? So what do you get that as? What is 2 power 10? 1024 minus 3 times, what is 2 power 8? 256, no? That's what I think. 256, which will be 3 6 18 1 15 16 1 6 7 1024 minus 768, which is equal to 14 minus 8 6. Okay, and 11 minus 6 is 5. Oh, okay, this is 256 probably. Yeah, so you'll get 256 as the answer. Okay, that is one way to do it. The other way would be probably by directly counting this subsets that do not contain both v1 v2. How do you do that? Okay, no, you need to do this process. Okay, it does not come directly, I think. The subsets that do not contain both v1 v2 means you are just counting
Is this the final answer?
yeah, this is the final answer, right?
No, but then the two vertices can also be selected in 8C2 number of the ways, because here you assume that there is an edge in between v1 and v2. It could be in between any other two vertices.
Yeah,
And-
it could be any two vertices, but for the particular question, one edge is fixed, right? So let's say
One
you
edge-
give me a graph.
Yeah.
You give me a graph, and let's say there is an edge between v2 and v3.
But then this one edge can be selected in 8C2 number of the ways. So therefore, the total number of the independent set. Okay, but even if one edge is given here, right? So yeah, fine.
This
And
argument will still hold. I'm just generalizing this process. If I simply assume that it is between v1 v2, the count will not change. I'll simply rename the vertices.
So initially I solved this problem using a slightly different logic. So I said that since there is only one edge, so only 8 vertices are remaining. So now the number of the independent sets could be I select no vertex, so 8C0, plus I select only one vertex in the independent set, 8C1. So basically I computed this sum as 8C0 plus 8C1 plus 8C2, 8 choose 2, and then 8C and settle 8C8. And this is the expansion of 1 plus 1 raised to the power 8, and the value came out to be 2 raised to the power 8. Initially, I thought the solution of this problem like this.
Yeah, but what if your subset contains, let's say, V1?
So my argument was that since there are 10 vertices and one edge is given, so now I am left with 8 number of the vertices in which there is no edge.
Yeah. So you have 10 vertices and
Yeah.
you have an edge here. So
Yes.
these are 8, I agree.
Yes. And now I can now to form the independent set, I can select none. So I can select none in the 8C0 number of the ways.
Okay.
And I can select
okay. Got it.
one
That
and
okay.
81 number of the ways.
So okay, you select none of them. Okay, you select one of them and so on, no?
Yes, yes.
And
then finally I select all 8 of them. So this is the sum of the binomial expression.
that is okay, but let's say this is V1 and V2 have an edge between them. Okay, well,
Yes.
and V3, V4, and so on till V10. If I say a set is V1, V3, V10, okay, this should be, so since there are 3 elements here, you mean the count will be
This will be the part of 8C3.
8C3, right? But in 8C3 you are selecting only from this set. No, only from the
remaining
8. But there is a V1 here, but V1 belongs to this. V1 belongs outside.
So yeah, but even if you select this V1, so I have excluded. Okay. Yes. So probably then its solution. I mean, in this way, it is not correct. Yeah.
Well, I think it's not that it's not correct entirely, but I feel like it should be a simple argument that again, like before, you are just fixing V1. So you are choosing V1 to be there or not.
So basically, since I'm only considering 8 vertices, so I have already fixed an edge in between V1 and V2, and now I cannot. So this V1, but still the answer is correct because it is same as that as if I fix the edge in between V1 and V2, or because we are not considering 8C2 factor there, because it is given in the question that there is an edge in between any two.
Yeah. So did you count 8C2 also? You should be counting, right? Because
yes.
I mean, you can choose something like that. Yeah. So yeah, so this is coming to 256. Is it?
Yes, this value is coming. Yes.
That is okay. That is strange. Because see, we are not. Your subset could be across this also. Yeah.
The thing is that these two statements are equal. That I consider an edge in between the vertices V1 and V2, and I only consider the remaining 8 possibilities. One thing. Similar to your solution, wherein you did not consider 8C2 factor. Why so? Because you, without the loss of generality, you assume that there is an edge in between V1 and V2.
So you mean there is an 8C2 factor outside this?
It could be. Yeah.
Okay.
If you consider that this edge can exist in between any two vertices, yes. I don't know whether this could also be a potential solution then.
Okay, sure. Yeah, I think it's just the interpretation that subsets do not contain both V1, V2, but your subset could contain, from as far as I understand, your subset could contain something like this. But I'll get back to you. Okay.
Yes.
Yeah, something seems. This approach should work, but I think that there is something that additionally needs to be taken care of.
Yes.
Okay.
Yes.
Okay. Great. Okay. Good. So next is this question. This is a simple question. What is the number of maximum independent sets of an undirected graph with 10 vertices and 1 edge? Same graph, but this time I want you to tell me five, 6, 8. Oh, perfectly written. Okay, good. So this time we want to say what is the maximum independent set, which means maximum sized independent set. Okay. So what is the maximum sized independent set you can construct here?
6, 8C2, 8C2, no, 8C2. No.
No,
So this will be 10. So 10C2, 10C2.
10C2.
10C2
No. Okay.
Because I would be having maximum the maximum size of an independent set would be equals to 8. So
Okay.
out of the 10 10 vertices, in how many different ways can I select 8 vertices? That is the point.
Okay.
So that the value came out to be 10C8.
Okay, 10C8. Anyone else? Where maximum size is 8. That's what you're saying. Anyone else? Okay, let's see. Okay, number of maximum sized independent set in this graph. Okay, so what is the maximum size independent set here? Let's check. In G. Well, say size of I equals 10. Okay, which is all the vertices. Okay, this cannot happen. Why? Because if I choose all vertices, that is I choose all the vertices, right? Because there are 10 vertices, I equals V. This cannot happen because who else is 10C9? Okay, so that cannot happen because there is an edge between V1, V2. Okay, but see, I is 9. Can that happen? Well, can I have an independent set of size 9? Well, yeah.
Yes, we can have an independent size of size is equal to 9.
Right. 8 elements I'll choose from here, from this large chunk, because none of them have any vertices. Now, what about the final one element? The 9th element I'll choose from here. Okay. I cannot increase it further because then I'll be including V1 also, which means that my set will have an edge. Okay. And can I find, so 9 is the maximum. Okay, fine. But can I have another 9 sized independent set here? Yes, I can. Again, I'll choose this large chunk here, which don't have any edges between them. And this. I won't include V2 this time. So, is an independent. Here, this is a maximum independent set. Maximum independent sets. Because size 9 exists, this is a maximum because 10 is not possible. That's what we saw. And so what are the sets? I choose V1. I don't choose V2. I choose V3, V4, and so on till V10. Or another set is I choose V2. I choose V3, V4. This time I won't choose V1. Okay. Can I choose any more of size 10? Any other independent set of size? Sorry, not 10, 9.
No, I cannot. There will be only two.
Yeah, because if I choose any other set, this means I'm including both V1 and V2. If I choose both V1 and V2, it won't be an independent set anymore. Therefore, number of maximum independent sets is equal to 2 is the answer. Okay, and you had written 8C9 nowhere. So why 8C9 does not work is because that 8C9 sorry, what 10C9 will not work is because it will also consider those subsets which will have both V1 and V2. Oh, sorry. Okay, you had written will be 2 only. Okay, sure. Okay, good. So is everyone clear with this? Okay. So this is another question on independent set. So I'll move on to this week's topic. Okay, good, Jyotirmay. Okay, good. So unless you want me to discuss this question, I'll move to the next topic. Okay, just let me know. Okay, so this is a simple concept of independent set only. Okay, and okay, now we come to this week's chapter, which is complexity. So it's okay, complexity. So well, so far what we've seen is we've come up with algorithms for several problems, right? So far what we've seen let's say flows, bipartite matching. We've seen randomizations, how randomizations can help, and well, we see that there are some problems, okay, that can be for example bipartite is not okay, yeah, maximum flow. Okay, I'll write bipartite matching. Okay, we saw that using flows we can come up with a positive time algorithm, right? Bipartite matching we saw in polynomial time we can get an algorithm, and what are the things that we see? Well, polynomial identity testing. Okay, we said in randomized polynomial time algorithm exists. Now, why were we even talking about randomized stuff? Because this we do not know any non-randomized, which is called deterministic. So deterministic algorithm not known until now. Okay, so now this brings in the question that okay, we had to go for techniques such as randomization. Okay, and what is causing us to go for these techniques while we are confident that we may not be able to find deterministic algorithms? Okay, in other words, okay, what we are asking is what problems are easy, okay, which loosely means I can do it in polynomial time, and what problems are hard. Okay, and loosely, okay, this means that okay, let's say poly time unlikely, so maybe exponential time. I'm not saying that by hard I don't mean that it will definitely take more than polynomial time, okay, but it looks like it may be a harder problem. Okay, but so this if we had such a system, okay, of classifying problems, then it would be very nice, right? I do not need to go about looking for a deterministic solution. I can go for randomized algorithms or approximation algorithms or other types of algorithms to actually solve those problems. Okay, and this brings in the idea about complexity theory. Okay, computational complexity. So computational complexity is a way to characterize problems in terms of difficulty to solve it. What do I mean by difficulty for now? There could be several ways, but in this, for the scope of this course right now is only on time. Okay, in terms of time, how much time does it take? Okay, so now we define a few notions, such for example P, okay, is a class of problems, and if you've done formal languages automata theory courses, then you can also call it languages. They are equivalent. Okay, set of problems or languages that can be solved by polytime algorithms. By polytime, I mean deterministic, no randomization business. Okay. Now, what do you mean? Okay, and here I have another example. Okay, what is called NP. Okay. Now, these are problems, again, set of problems or equivalently languages that can be whose solution, okay, sorry, can be verified in polynomial time, deterministic. Okay, and this N stands for non-deterministic. Okay, set of problems whose solution can be verified in polynomial time. Okay, now what is an example of this? Let's say take let's say a given graph. Okay, this is called the reach problem, reachability. Given graph and S and T vertices, S and T, check if there exists a path from S to T. Given a directed graph, let's say, you want to check whether there is a path from S to T. Can you come up with a polynomial algorithm to do it? You are given a graph, directed, let's say, and you are also given two vertices, okay, S and T, which belong to the graph. You want to check whether there is a path from S to T. Can you come up with, yeah?
DFS?
You could do DFS, BFS, right? Good. So simply do DFS on S. Then what do you get? You get like a tree, okay, on S, and then you, okay, and so on, and so on, and somehow if T is reachable, then definitely it will be visited by the DFS algorithm. DFS will never skip it. Simply do DFS. If there exists a path from S to T, then T will always be reached. How much time does DFS take? Time taken is something like order V plus E, right? And v plus e is like the size of the input, so it takes polynomial time on the input size. Remember, input is given in binary. Okay. Now, so what does this mean? This means that reach has a polynomial time algorithm. So reach is in P, deterministic polynomial time algorithm. Okay, there is no non-determinism. There is no randomization. Okay, and now what about NP? What about, is it an NP? So what definition did I say that about NP? Set of problems whose solution can be verified in polynomial time. Okay, so now is can I give so you asked if there is a path from S to T. Okay, what I can do is, here is another version of the problem. You can always give me, if the answer is yes, there is a path, you could always give me a path and I could easily check whether that path goes from S to T. Okay, so given a path P such that S, okay, such that valid path, okay, such that the path starts at S, ends at T, then I can always verify. I just look at it step by step. Okay. Then I can always verify by going through the path in the graph. I can always go through the path in the graph and check if path is valid. So solution can be verified. So how much time does it take? Time taken is, the path length can be at most the size of the graph, number of vertices. So time is order n, which is still polynomial. So since it can be verified in polynomial time, I'll say this reachability problem is also in NP. Okay. Now, so does it mean that every problem which is in P also is in NP? So let's look at another problem. Okay, let's look at okay, Sudoku. I hope you guys have played Sudoku once in your. So if you've not played, I'll explain the game. Do you guys know Sudoku? Or is there someone who does not know what Sudoku is?
So what happens in the Sudoku? I mean,
Okay.
do we?
So Sudoku is a game which is like a 9x9 grid. Okay. 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, 6, 7, 8. Okay. 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay. So it's like a 9x9 grid. Okay. And okay, so let's assume there are lines here. Okay. And further there are grids like this. And you know, there are 9 rows, 9 columns. Okay. And there are like numbers here. For example, 2, 9, 3, 6, let's say 5, 8, 1, 7. You can, it's a fun game to play, not 13. It can't be more than 9. And so there are numbers here, okay, and so on, filled. Some of them are filled, some of them are not filled. There are gaps in between. The game is, it's not a game, it's a puzzle technically. So the puzzle is solved when you fill all the numbers, fill in the gaps with numbers, fill in the gaps with numbers, okay, fill in the gaps with numbers such that uh, 1 to 9 appear exactly once in each row, each column, and finally each box. What is a box? Well, these. Okay. So it used to come in newspapers, but I don't know nowadays whether it comes or not. But it's a fun game to play. You just need to keep filling you to some kind of trial or error and so on, and then fill the gaps with numbers, and then try to solve the entire Sudoku. Okay. So for example, maybe I can do a search here and do Sudoku, and then look for images, and this is what a Sudoku looks like. And then you fill in the numbers, and finally the solution looks like this. Observe that every row, look at the first row, there is 1, 2, 3, 4, 5, 6, 7, 8, 9. Each of the numbers from 1 to 9 appears exactly once. If you look at any column, look at the first column, 9, 6, 2, 4, 1, 5, 3, 7, 8. Numbers from 1 to 9 occurs exactly once. Okay. The black ones are, given by the puzzle itself, and the brown ones here are filled by the, game player, the puzzle player. Okay. And if you look at this box, 3 by 3 box, which is highlighted in brown. Okay. For example, the first box has exactly one occurrence of 1, 2, 3, 4, 5, 6, 7, 8, 9. So this is an example of Sudoku. Okay, but what are we interested in? If I ask you, is Sudoku solvable? If I give you a Sudoku, given Sudoku puzzle, okay, give an algorithm to solve it. Okay, if you do this, then I can always do this. Okay, there are 9 choices for the first box, and for the second box there are 9 choices, or you can say 8 choices if you want to do a little bit better. Then for the next box there are again, and so on. But let me give a simple bound. So 9 choices, 9 choices. I just go across all possible. I'll do what is called a brute force. No. So brute force equals 9 choice for each box. Okay. And for each box, and how many and I put 9 choices here times 9 choices here times 9 choices here, and so on. So 9 times 9 into 9 power 9. Here this is the number of boxes. Not number of boxes, sorry. I'll do 9 choices in the first box, 9 choices in the second box, and so on. Okay. And so on, which is 9 power total number of boxes. And how many boxes are there? 9 cross 9. So you will say, oh, 9 power 81, and which is constant. So you say, okay, it's doable in polynomial time. So it is in P, but this is not the Sudoku we are talking about. The Sudoku we are talking about is given any n cross n. Oh, okay, now it's a complex problem. Okay, here let's say S is a Sudoku puzzle. S is a Sudoku puzzle. N cross n Sudoku puzzle. Instead of 9 cross 9, I'm giving you a n cross n Sudoku, which is totally fine. If n is, let's say, 15, then you have 15 by 15, and each of the 15 rows should have 1 till 15, and each of the 15 columns should have 1 till 15, and so you can define it that way, no problem. Now what do you have? Well, brute force approach, what does it give you? It gives you n times n to the n. Oh, and this is bad. N to the n is really bad, because n to the n is equivalent to n times n to the n is equivalent to 2 to the n log n. So this is exponential. Okay, so, and in fact, do we know better algorithms for this? Maybe, but we have not got better than exponential. That is for sure. Maybe you can shave off this log n part, but it has never gone down below exponential. Okay, so no known polynomial time algorithm, deterministic polynomial time, deterministic polynomial. Okay, but now I ask you the same question. Now, can its solution be verified? Okay, this is the first part. Second part is, so okay, firstly, so no known deterministic. So Sudoku is in P is still not known, and if is solution efficiently verifiable? That is, if I give you a solved, so if I give you a solved Sudoku, okay, so what is the problem? Okay, what is the problem that we are trying to solve? In the original Sudoku, the decision problem we are trying to solve is, does there exist a solution for this given Sudoku or not? Okay, I want to make that also clear, because that is important foundationally. Okay, so this is the problem is as follows: given some puzzle S, okay, is it solvable? Okay, so S is not this a Sudoku puzzle. S is a Sudoku puzzle solvable, because there could be invalid Sudokus, right? So given a puzzle S, is it solvable or not? That is the question. Okay, and so which is equivalent to asking, which is equivalent to saying, does S belong to Sudoku n cross n or not? Okay, so I'm just saying that membership in a language is same as solving a problem. I mean, deciding whether yes or no answer to the problem. Okay, so is the solution efficiently verified? Well, you give me a solved Sudoku, simply check all n rows, okay, and n columns and n boxes. Just check whether all are just 1 2 3 4 5 6, all 1 2 3 4 5 6 7 8 till n appears exactly once, all of them, and say yes or no. So it's easily checkable, because how much time does it take? Time taken is order n cube, where n is actually the number of rows here, but it's okay, which is polynomial. So what do you get? You see that Sudoku is in NP. It can be verified easily, but can it be solved easily? We do not know whether it's in.
So would it be of the order of n cube in the verification, or of the order of n raised to the power 4? Why so? Because for every element, I need to make n number of the rows and n number of the columns.
Yeah, that's right. So let me just to clear the confusion, I'll make it k cross k. Okay, so k cross k Sudoku, k cross k, because n would usually be reserved for the input Okay, so this is some k cross k. Okay, and so it should not be taking n cube. It'll. So what I meant was k cube. Yeah, yeah. Well, is this fine?
But still, so for every element, I would be making k number of the checks towards towards the row side, and k number of the checks towards the column side. So for every element, I need to make k square number of the checks, whether the element is at the right position or not. Isn't
That's
it?
right. Okay, okay. Yeah, yeah. That makes sense.
So then, how many elements are there in the Sudoku puzzle? There are, say, k square number of the elements in total. So therefore, k square into k square, and the value came out to be k4, I guess.
Yeah. Times k. For each row, you are going across k elements. For each column, you are going across k elements.
Yes, yes.
And for each box, you are going across k elements. So there will be an additional factor of k. Yeah. Good.
Yes.
Okay. So Sudoku is an NP. So now here is let's call it a theorem. Okay. P is always contained in NP. Okay. P is contained in NP because that means anything that can be solved easily, that can be verified easily, but the other way around, this is not known. So this is you could call it a conjecture. It has not been proved till now, and so of course, if you show that P is contained in NP, NP is contained in P. Let's say you show that NP is contained in P, then you show that P is equal to NP. Now, if you show this, then it will have very big implications. It means that so many problems that we thought are hard actually suddenly becomes easy. Okay, and I mean there are a ton of stuff that will happen. Practically, what will happen is one good thing that will happen is that all these hard problems will become easy to solve practically, but it also has bad consequences. For example, this in cryptography. Okay, what is cryptography? Well, you have a message that you want to encrypt, and it through one F, let's say, then it becomes F of that message. Okay, and this is generally easy to do. But going back from hard to easy, going back from the encrypted message to the original message, that is decrypting, is hard. It is very hard to do. So how do we choose a candidate for the message, the encryption? Well, we'll choose a very hard problem in the decrypt. Okay, for encrypt for doing the decrypt, for the opposite process. The opposite process, we choose the hardest problem in NP. So we look for these kind of functions which are easy to encrypt but very difficult to decrypt for an outsider. Of course, if I have some pin, okay, then I'll be easily able to decrypt it. But so this is the kind of setup that I have for cryptography encryption, and this is used by banks and online accounts, Instagram, Facebook, whatever. And this is the setup that they use. And if it so happens that it is proved that P equals NP, then suddenly the opposite process, that is decryption, becomes easy. So what does that mean? This means that the security of all these what are so-called secure protocols will be compromised. So there'll be a huge disaster if we know that P equals NP. And and by the way, an interesting thing is, so I told you, so it should not always be difficult, right? Decryption, at least for the person who is encrypting, the decryption should be simple. Otherwise, it will be very unusable. Because if you, let's say you are encrypting your password, let's say the company encrypts your password. If I send my password, then it should be that my password is easily checked, and then I get authentication, right? So that process should be easy. And what is that process of me giving my password and checking? It is simply this verification process. Is the solution efficiently verifiable? This solution that is efficiently verifiable is often also called a certificate, or also called sometimes a witness to an NP problem. This is a witness to an NP problem, and this is exactly what is happening here. My password is my certificate here, because the password is is the certificate to this problem, hard problem. The hard problem resides in NP, which means that if my certificate is valid, if my solution is valid, it is easily verifiable. If my solution is not valid, then it will easily, in short amount of time, tell me no, it is not valid. Okay. So this is an example. Okay. And so this is, so far this is the picture. So far this is NP, and we have P sitting in it. We don't know if P equals NP. Generally, it is accepted that P is not equal to NP, but we don't know that. No one has proved it yet. Okay. So okay, so that is out of the way. Now, what do you have? Well, we can talk about another language which is called coNP. Okay. Now, what is coNP? So it is consists of complement of problems in NP. Okay. So, and what is the complement? It contains the complement of problems. I mean, set complement. All the languages which are not in so okay. What is a nice way to state it? I don't want to introduce too much maths into this, so that's why. So what I mean is, all the yeses in NP will become the no's. Okay. So, for example, we talked about reachability, right? Equal to graph and ST such that there exists a path in G from S to T. And reach complement will be all those graphs and ST such that there does not exist a path in G from S to T. So it's a complement event. So coNP is, so coNP is consisting of all the languages or problems L such that the complement of L is in NP. Okay. Now let's so now what do you have? We know P is contained in NP. Question is P contained in coNP? Okay, that is the question. The answer is yes. Why? Because for any language L in P, L complement is also in P, and we already know that P is in NP, so its complement will be sitting in coNP, and so the complement language is also in P. L complement is also in P, so therefore P is in coNP also. I'll tell you more in detail. So P is contained in coNP. So so why is P contained in coNP? Okay, reason. Okay, say some arbitrary language is in P. Then there is an algorithm A that solves L and runs in polynomial time, deterministic polynomial time. So claim is there exists a deterministic polynomial time algo such that L complement. What is L complement? Um, so for example, reach complement was there does not exist a path of the form. So all the complement instances, okay, whatever is not contained in the set L. So L complement runs in okay, deterministic so that L complement solving as L complement. What is that algorithm? So algo for L complement is simply run the algorithm A. Then it will output yes or no. If A outputs yes, then output no. If A outputs no, then output yes. So what will happen? Its behavior is exactly opposite to what L does, right? Which is since A computes L, everywhere it's the input belongs to the language L, it will say no, and the original algorithm A will say yes, but we'll say no finally. And if it said no, then we'll say yes finally. So it's the final language computed is L bar complement. So therefore it means that L bar is in P. Okay, so since L bar is in P, it means that L bar is in NP also, because P is contained in NP. No? And since L bar is in NP, what is L? L is in coNP. Okay, so which means that if L is in P, then L is also in coNP. So now our picture becomes like this. So this is NP, this is coNP. Now now P is sitting here. If a language is in P, it should be there in coNP also. If it is in if it's a language in P, then it's both contained in NP as well as contained in coNP. But if P is exactly NP intersection coNP, we do not know. So what does that mean? So here's another theorem. P is contained in NP intersection coNP. Okay, and this is a theorem. And whether P is exactly equal to NP intersection coNP is not known. And whether whether NP is equal to coNP, this is also not known. In fact, the fact that P is not equal to NP intersection coNP is the general accepted, or so I believe. And I think you know Jack Edmonds, no? You remember the Edmonds-Karp algorithm we did in week 2? He is a he does algorithm design and complexity theory. He believes in this conjecture so much that he has, there's a picture of him with a rock which has it carved onto the rock. If you can, I can quickly show it to you maybe. Yeah. NP, coNP. Here. So yeah, this is what he believes in, and he has even carved. This is Jack Edmonds, so he has even carved it on a rock outside his house. Anyway, but of course we do not know the answer to it. Now, okay, anything else? Okay, this I think this required a lot of build up. Okay. There is final one concept, okay, that needs to be covered, which is the concept of reductions. Okay. Okay, please bear with me. It's about to be over now. The concepts at least. Then we need to solve the problems. Okay. So what are reductions? Well, reductions are a way to transform one problem to another. Problem to another. So I'll quickly give an example of carp reduction. Okay. Carp reduction. Okay. Or a polynomial time carp reduction. Okay. Poly time carp reduction, or also called many one reduction. So polytime many one reduction means that if we say problems A reduces to B, that is shown by A P M B. So this means polytime. This means many one, also known as carp reductions. Okay. B, if for every input x to A, okay, x is in A, and okay, for example, there exists a sigma, okay, which takes in a string, this and outputs another string, such that x is in A if and only if sigma x is in B. What does that mean? Well, it means that if algorithm for A says yes, then on X. Algorithm for B says yes on sigma X. And similarly, if it says no on X, then algorithm for B says no on sigma X. Now, what is the advantage of this? This is a way of showing hardness of languages, because see, if why does it show hardness of languages? If I have this is what it means. If I have an input x, I can pass it through a filter. Okay, I can pass it through a filter which gives sigma of x. Okay, and to a algorithm solving B solver, and it says yes, then my bigger algorithm will say yes. If it says no, then bigger algorithm will say no, and therefore I get an A solver from it. It simply means this: solving B is sufficient to solve A. Solving B is sufficient to solve A. So if B is easily solvable, then A is easily solvable. If B is easily solvable, then A is easily solvable. So in some sense, it means that it appears that B would be harder than A. Yeah, I mean, okay, if now the idea is, okay, now let me copy this. If A is hard, if A is hard to solve, okay, this is denoted by A reduces to B. Okay. So A is reduces to B means that B is easily solvable, then A is easily solvable that way. Because using this box diagram, you understand that reduction means that if I have a B solver, then A solver can be done easily. Okay. Oh, by the way, the sigma process, this should be computable in polynomial time. Sigma computable in polynomial time. Okay. Anyway, if B is easily solvable, then A is easily solvable. Then if A is hard to solve, then it must be if A is hard to solve, then it must be that B is hard to solve. Because if B were easy, then A is easy by this. So A cannot be hard. So you see that this reduction is a way to talk about hardness. No? So therefore, A, when one reduces to B, sort of means that B is at least as hard as A. That's why there is a less than equal to sign.
So the thing is that if A is getting reduced in
sorry, A is at least. No, B is at least as hard as A. Right? Yeah, go ahead.
So if A is getting reduced to B, then it means that B is at least as hard as the problem is.
B is at least as hard as the problem A is. Because if B was not as hard as A is, B were easier than A is, then even A would be easy.
Yes. And nothing can be said about the hardness of the problem B except that this is at least as hard as the problem A is.
Yeah. We are not yet saying that B is strictly harder than A. Yeah.
Okay. So can we have, those problems as an instance of B and which are, even tougher problems, like say the problems which are there in, say, taking the exponential time or even higher in the hierarchy than the NP class problems.
Okay, can you repeat your question?
So the problem B may belong to a complexity class and which is higher than the NP complexity class, and say something like say is taking exponential time or not only the exponential time, but then space wise also taking are really tough.
Yeah. I mean, those are called separations, and those are about languages which are strictly more harder. Let's say more harder than NP. Do these problems exist that are strictly more harder than NP? Definitely they exist. So reductions also have a limit. Okay, they can show only at least as hard, but they can't show strict amount of hardness, which requires finer tools, better tools to actually characterize that. But that is out of scope of this theorem. But there is something called time hierarchy theorem that actually tells that there are much more harder. You can always find more difficult languages than any example you give. I can always give you a more harder, strictly more hard, which means will always take more time.
Yes, because something is required to determine that whether this problem is strictly harder. I mean, some effort, some time is required that this is even harder than this thing. So, I mean, who is going to decide, and what is the decider, and who is the decider who is going to decide that this is strictly harder or maybe equal to the level of the hardness.
I know, but that is a notoriously hard problem. I mean, if if we could do it for anything, we could do it for P and NP also, and show that P is not equal to NP. We can, right? But that the separating classes is actually a very tough job, and it's a notoriously difficult task. And these are what are called lower bounds also. If you show lower bounds, for example, circuit lower bounds and so on, if you show them, then you it is possible to show, but it the progress so far is very thin. We've not been able to. I mean that is the aim eventually, but I mean it may take centuries before we even get close to doing those stuffs in easily.
Okay. Yeah. Fine.
Okay, so oh, just a moment, I need to charge. Okay, so what are the questions? Oh, okay, it's all sad and stuff. Okay, this week's content requires a lot of background, so I think I should have started earlier. Okay. Okay, good. Okay. Okay. So now we have the notion of hardness. Okay. So now question is, so if A reduces to B, says that B is somewhat harder than A. Okay, appears to be harder than A. Then what is the concept of the hardest language in NP, or equivalently P, or coNP? Say, so that is what is called hardness. Okay, now that is what is called hardness. That is something like NP hard, P hard, coNP hard. Okay, so okay, so actually hardest language in, okay, I'll be very loose with this, but okay, so if for all, okay, for all languages in NP, okay, you can similarly extrapolate this to P, coNP, whatever. If L reduces to some language A, then A is called NP hard. Okay. Further, if A is belonging to the class NP, then A is called NP complete. So think of completeness as a candidate representing a class. So this is NP, this is P, this is coNP. Okay. So there are so many languages out here. Some are in P also. Now you take one guy such that every other person in NP reduces to this one guy. If this guy was sitting outside NP, it would be NP hard. Okay, if blue reduces to green, then green is NP hard. Everything in NP reduces to green. But if everything blue reduces to red, which means because red is already sitting inside NP, so it means red is NP complete. Okay, and NP complete sort of represents that class NP. What does it mean? Now, why is NP complete? Let's say A is NP complete. What does it mean? It means, so for every language L in NP, okay, L reduces to NP, L reduces to A. Now, if it so happens that someone comes up with a polynomial time algorithm for A, if it is shown that A is an NP, if it is shown that A is an NP, then for each of these language L, they become solvable in polynomial time suddenly. Sorry, what I was saying. If A is in P, then L is in P, because A is the smaller box. A is this box here. Okay, the terms are changed between B and A, but if this box is solvable in polynomial time, and since sigma is solvable in polynomial time according to definition of reduction, this entire box is solvable in polynomial time. So therefore we have that this language L, I mean any language L in NP actually falls down to P. That is, any language in L falls down to P, which means any language L in P NP falls down to P, means that you show that P equals. So therefore NP complete languages are a way to actually show that P equals NP, which is unlikely, but yeah. So do we know? Yeah.
Can this green dot ever be there inside the circle? Can I write this equation that NP complete is equal to the intersection of NP and NP hard?
NP complete is equal to intersection of NP and NP hard. Yeah, you can say that.
So if that is the case, because there would certainly be some problems in the NP itself, and wherein all the problems which are there in NP are getting reduced to, and those problems are called NP complete, it is okay. But then in the definition of the NP hard, it is just mentioned that all the problems can be reduced to, all the problems which are there in NP, if those problems can be reduced to a problem, that problem is NP hard. And then thereafter we see that whether that problem belongs to NP itself or not.
Yeah. So red is NP complete as well as NP hard.
Yes, that will make more sense. Yeah.
That is a good thing that you clarified. Yeah, before I. Yeah.
Right.
So what? That's good. Yeah, actually, that is important. That if where do I put it? That a language A is NP complete if 1, A is NP hard, and 2, A is in NP. Yeah, good that you mentioned that, because I had forgotten about it. Yeah. So okay, good. So this is about NP completeness. Do we know candidates that are NP? Yes. SAT is one example. What is SAT? SAT is given a Boolean formula, check if it has a satisfying assignment. Okay, given a Boolean formula, check if it has a satisfying assignment, and that is sad, right? Now, for example, x1 and x2 or x3 and x4 x3 complement okay, so this is the given formula. Is it possible? Well, if I set x1 equals 1, x2 equals 1, and x3 equals 0, then okay, this is, I'll call it phi. Okay, then phi equals 1. That is, it is satisfied. Now, given a Boolean formula, checking whether it is satisfiable or not, that is an example of NP completeness. Another example given in lectures is independent set, maximum independent set. Set, that is, in set is a set of all subsets of V such that, okay, not only okay, and some K, okay, and such that this is a bad way, G and a K, okay, there exists an independent set I of size at least K in G. Okay, this is called the max independent set problem or ind set. Okay, and what is the problem version? This is a language version. What is the problem version? Given GK, check if there exists an same thing independent set I of size at least K in G. Okay, this is another example of an NP complete. Okay, so for the proof of this, check the lectures. But to prove this, you need two things. No, you need to show that it is in NP. And can you say SAT is in NP? We can say SAT is in NP because if you give me a satisfying assignment, I'll just plug in that to the formula and then start evaluating each and or, and then in polynomial time I'll get it. Max independent set, yes. Is it in NP? Yes. Why? Because like I said before, you give me the set of vertices, and then I check whether there is any edge among them or not. If there are no edges among them, then I'll say yes, the set you give is correct. So the certificate, okay, the verifiability is easy. Okay, so it's in NP. NP hardness, you need to prove that everything reduces to this, or okay, since A reduces to B, B reduces to C, implies A reduces to C. Therefore, saying that A reduces to B and A is NP. Okay, let me call this a theorem. A is NP hard, then B is NP hard. Now let's say B was in NP, then B is also NP. Okay. Okay, so we've covered all the background. Okay, I'm not sure how much I'll be able to cover. There are only 10 minutes left. Okay, but there was a lot of concepts I read. So okay, so here are the questions. Let's quickly solve them. Okay, So which of the following are true? SAT is in P, then 3 SAT is in P. Okay, so this was done in the lectures. Okay, so note that 3 SAT, what is 3 SAT? 3 SAT is what is given 3 CNF. What is 3 CNF? 3 CNF is of the form and this is called conjunctive normal form. So there's a conjunction at the top. Conjunction means and. So AND gate followed by OR gates below, and each of them are 3 below. This is what it always looks like. So there are 3. So here it's x1, x2, x3, x2, x3, x4, let's say, and so on. So this is 3 CNF. Note that this formula does not look very tough, right? It's very simple. It's very it can this is the diagrammatic way to show it. It can also be written as a formula as x1 or x2 bar or x3 and x2 bar or x3 or x4 and so on and so forth. Note that each of them are 3. Each of the size of each what is called clause is 3, and this is called a 3 CNF. You want to check satisfiability. Check if, let me call it 3 CNF is satisfiable. So before it was any Boolean formula, right? Now I'm restricting it to 3 CNF. So it so happens that 3 SAT, which is 3 CNF satisfiability, is NP complete. So even when we reduce the clause to 3 literals, it is so hard. It is NP complete. So even this simple, humble looking circuit formula is so notorious. Okay, 3 SAT is NP complete. So if SAT is in P, okay, so now if 3 SAT is NP complete, which means SAT reduces to 3 SAT. Okay, SAT reduces to 3 SAT. Now if, what is the question saying? SAT is in P. Okay, now if SAT is in P, then 3 SAT, then okay, sorry, it's SAT is 3 SAT. It also means that since both of them are in NP, it also means, okay, wait, sorry, and also 3 SAT reduces to SAT. Now since 3 SAT reduces to SAT and SAT can be done in P, then 3 SAT can also be done in P. So your answer is yes, it is true.
But then 2 SAT is there in P and
yeah, that is in I've put that in another question. 2 SAT is a different case because 2 SAT is not NP complete. I mean, it's not known to be NP complete.
yes.
But 3 SAT, we know that it is NP. There's a proof that 3 SAT is NP complete. 2 SAT is easier. 2 SAT is NP. Okay, so P equals NP, then SAT is in coNP. Is it true? Okay, this is A. Now what is B saying? B saying P equals, yeah.
Yes, true. It is true.
Then SAT is in coNP. Well, if P equals NP, suppose P equals NP, also we know that P is in coNP. Now what does P is in NP equal to NP mean? That everything in NP is also in P, which means SAT is in P. So we know that P is in coNP, so which implies that SAT is in coNP also.
Otherwise, also P is equal to copy. So
P is equal to copy. Yeah, that is another way to do it. Okay, and P is equal to NP intersection coNP.
We don't know.
Right, I already said P equals NP intersection coNP, not yet. Okay, so not known. P is contained in NP intersection coNP. Now this is known. This is true. P is contained in NP. True.
True.
NP contained in NP. P not known. Okay. Um, P equals NP, then P is equal to coNP. Again, so which question is this? G. P equals coNP, then P equals NP, then P equals coNP. P equals NP, then P equals coNP. Well, if P equals NP, and then NP equals co-P, or in other words, P is since P equals co-P, NP equals, since P equals co-P, which means even on complement, it's just a matter of flipping yes or no. Then anything that is in P, anything that is in NP, the complement is also in NP, is also in P, right? So on complementing, still in P. But we already know that NP, the complement of NP is equal to coNP. No, for any, okay, I'll write it. For any L in NP, okay, L complement is in coNP. But by assumption, L is in NP, L is in P, and so L is in co-P also. So L complement is in co-P, so L complement is in NP. Okay, so L is in coNP. Okay, so any language L in P, okay, any language in L in P which is equivalent to P, okay, is equal to coNP, is in coNP. Now A is in P, then A is in NP. True. You can any P, because P is contained in it. A is in P, then A is in coNP also. True. P lies between, in the intersection of P and coNP. Okay. Maximum bipartite matching problem is in P. Okay. So any answers for this?
Maximum bipartite matching problem is in P. I forgot this problem was, but I remember it was in P. It was in P.
Okay. Yeah. So oops, sorry.
Because it was having something to do with the length of the cycle also, and maximum bipartite matching.
Maximum bipartite matching. We saw algorithms to solve it, and
Yes.
one algorithm was simply by using flows. No.
Yes. Now I remember. Yes.
Yeah. Yeah. So one way to do it was using flows, and it flows. What is the time taken? Is something like n to the 4, n to the 6, and all. Ford Fulkerson, Edmund Karp, and so on. Yes. So done in week 1, maybe, I think.
Yes.
Week 1 or 2, somewhere. We've given polynomial time for this. Independent set is in P.
No.
Not known, yeah. Because if independent set were to be in P, then P will be equal to NP because independent set is NP complete.
Yes.
Now 3 sat is NP hard.
So do we have any problem in NP which is not NP complete?
Oh no, if we knew that, then we would say that NP is not equal to NP. No?
Because most of the problems, because NP complete problems are the monitor problems of the NP class, representative problems of the NP class. The toughest
Yeah,
problem in that
not
in
only
the
that.
class.
If we say that, oops, again. If I tell you that there is a language in NP which is not known to be NP complete,
Yes.
and but that will it prove a separation? Oh no. Okay. Yeah, it's not known, but even if it is known, it won't show that P is not equal to NP, right? Because
Okay.
it will just show that NP complete and non-NP complete are very disjoint. Yeah. Okay. Oh, okay. No, it will show that P is cannot be that P is equal to NP. Huh. Yeah. It will show that P is not equal to NP if you show a language which is not NP complete. Why? Because if it so happens that P is equal to NP, then is it not true that all the languages will be? Oh, okay. No. Forget about it. I'm sorry. I'm confusing you. It won't show.
Yes. Yeah.
Yeah. Okay, so this is done. 3 sat is NP hard. Yes, 3 sat is NP hard because 3 sat is NP complete.
Yes.
Okay, it's already 8. Okay, DNF sat, let's forget about it. Okay, let's quickly do this. Let K sat be the problem of deciding if K CNF is satisfiable or not. Then show the following. For any K is at least one K is in NP. This is true. Okay. Why the certificate is the satisfying assignment. Now, what does KSAT mean, by the way? KSAT means that you have a CNF. You have a CNF where instead of 3 CNF, where every OR has 3 elements, you can have something like 4 or 5 or whatever. K many elements. K variables. K inputs or variables, yeah. Actually these are called literals. So this is like x1, x2 bar, x3, x and so on, x4, x5 and so on. So this is a key CNF. Okay, is it in NP? Yes, it is in NP because just the satisfying assignment, if you give me, I can easily verify it. Now show that one sat is in P. Okay, show that one sat is in P. Now what is one sat?
I mean, every clause is having just one variable.
Right. Check if one CNF is satisfied. So it will, what does one CNF look like? It will look like this. Now it's something like x1, x2 bar, x3, x4, again let's say x1 and so on. This is what one sat looks like, no? But notice that it's feeding into OR just as a single line. So what will OR give? So OR will just give whatever the input is giving, right? Because what does OR say? OR will output 0 if all inputs 0. Otherwise 1. But if OR has a single variable as input, then the only case when all inputs are 0 is when the variable itself is 0. Otherwise, it will output 1. So, which means that if x1 is 1, then OR will output 1. If x1 is 0, OR will output 0. Right? So, OR of single variable xi is equal to same as outputting whatever xi itself is. No? Literally. So this guy this guy is same as AND of OR of no AND of remove the OR gates and write x1, x2 bar, x3, x1 and so on. Just remove this and just pull the literals up, because anyway OR was not affecting the computation only. So what do we get? We just get a single AND, right? And this is easy to compute, right? And what do you do? Check. Okay, now what sorry, what is the satisfying assignment? So satisfying assignment is when so for AND gate to output 1, then all of these should be 1, no? So x1 equals 1, x2 bar equals 1, which means x2 is equal to 0, and x3 equals 1, and so on. This is a satisfying assignment. If it so happens that there is, let's say, an x1 as well as x1 bar, that is the only case when there is a problem. So what you do is simply check if there exists xi bar. Okay, there exists xi bar feeding into AND. If yes, output no, otherwise output yes. So you agree, right? So please let me know if you don't understand. Okay, I just explain it quickly because of lack of time. Okay, so now we have one sat done, two sat is NP. Now I don't have enough time to do this, but this is true. Okay, check proof somewhere. Okay, it's a reachability argument. You transform each OR clause. So what does two sat look like? Every OR has two inputs, right? You write it as an implication, A implies B, and then you draw a graph and checking reachability is final. Anyway, okay, so two sat. Okay, this is slightly difficult, so I won't do it right now. Is it currently known that two sat is NP complete? No, because we just said that two sat is NP. If it was known that two sat is NP complete, then P equals NP. Finally, 4 sat is NP complete. Now this is the final thing I'll show, then we'll stop. Okay, 4 sat is NP complete. Yeah, the answer is yes. Why? Because yes, why? Because you can show that 3 sat reduces to 4 sat. How? Well,
Are you using a dummy variable?
yeah, that's what. So we have AND of ORs, and we have 3 sat, 3 CNF. Okay, originally x1, x2, x3 bar, x1 bar, x2, x3, and x3, x4, x2, 2 bar, and so on. Now what I'm going to do is I'm going to duplicate one of them, x1. I'm going to duplicate, let's say, x1 bar. I'm going to duplicate x3. So duplicate one input in each clause. Okay. Then what do you get? Then we get a 4 CNF. Okay. And if say x1 or x2 or x3 bar, notice that this is same as x1 or x1 or x2 or x3 bar. Why? Because a variable oring, or an OR operation between the same variable will give you the same variable. No, so same is happening here. Okay, so duplicate will not change it. In fact, we get a 4 CNF, so even the satisfiability will be preserved. So it means if this is satisfiable, then 4 sat is also satisfiable. The this duplicated one is also satisfiable, and if it is not satisfiable, then it cannot be that this is satisfiable. So what do you get? Well, we get that 4 sat is NP complete. In fact, using this concept, you can even show that 5 sat is NP complete, and 6 sat, and 7 sat, and so on, k sat. So you get that for one, okay, 1 sat, 2 sat are in P, 3 sat, 4 sat, 5 sat, and so on are NP complete. Okay, having said this, okay, I'm done. So if you have any more questions, please stay back. Okay, I know it was a very, I ended it in a very hurry. Okay, there were a lot of things to cover. But if you have any questions, then please let me know. Okay, or we'll end this session. Okay, so I hope what I taught was clear. Sandhya, is it fine? Hello? Sandhya? Yeah, Goel, you were saying something?
No. This was a very lengthy session and lots of content. Yeah.
Yeah, I mean,
I did first two problems in independent sets. Those problems were really good.
oh, okay. Yeah, okay, thanks. Yeah, it's well, it's cramming a lot of complexity in a single week content. So therefore, it's a lot of content. It can be overwhelming. I think that's why people have left already.
Yes. And what will you be covering in the next session? Which topic?
I believe next session is approximation. Yeah, I think it's approximation algorithms or parameterized. I'm not sure. Need to look into it.
Okay. Yeah. Fine.
Yeah.
Right then. Thank you so very much. Then, yeah. Thanks a ton for this session.
Oh yeah. Yeah. Okay. Thank you, Goel. Yeah. Okay. Thank you. Yeah.
Bye. Good night.
Okay.
Bye.
Bye. Good night. Sandhya, are you in the call? Okay, then we end the session.